Hi, everyone. Oh, that worked really well. That was tactic number 2. Hello. Welcome to our talk. We're happy to be here today. We're going to do a little walk down history and see the giants before us that helped us to come to where we are today. My name is Quinn. I'm an engineering manager at Dapper Labs. Try to make the workplace more fun and the web a bit more open.
Hi, my name is Furkan. I work at Autodesk, and I work on a product called Alias, which is used to design the cars that Kate was talking about driving just this morning. So there's an exercise that I like to do every now and then. I pick a random moment and then think back to all the things that I had to do and all the things that had to happen to me and all the things that I had to go through to end up in the moment that I'm in right now. It usually helps with gaining a different appreciation. It's like, oh, like I wouldn't have met this person if I hadn't made that decision, which was caused by some other decision, some other thing that happened. And it's a whole network of things that you can just go back forever. And as I was reading a book recently, I came upon this quote from Fred Rogers. And I thought this is a great way of starting the talk, because what we'll be doing from now on is taking a moment, like freezing this moment essentially for the next 40, 50 minutes, and then asking the question, how did I get here? How did we get here? Especially as software engineers and computer science and all the technological advancements that resulted from computer science related advancements. We'll be talking about a lot of these people here, except one. If you notice it, please let me know. But if you don't see somebody that you would have liked to see here, it's not because they didn't deserve to be here or anything. There were a lot of people to choose from. And at some point, it's just luck that somebody was here and somebody was not. So please don't be offended. So along the way, as we were preparing this talk, we tried to create a graph of dependency. And if this was your project dependency, you would be mad, like, dealing with all of this stuff. But all of these people, like you'll see the names, Charles Babbage, Dennis Ritchie, Ken Thompson, all of these people is essentially our dependency graph, the people that we depend on, their contributions that we depended on, so that we can build the things that we're building today. And as we're looking back, we'll have to pick a starting point, and the starting point that we picked is, this stopped working now, is Charles Babbage, the father of computers. He built the first programmable computers. He was born in Britain, UK. He was born into an affluent family, banker father, and he had a good school. And he went to University of Cambridge. He was very mathematically inclined, polymath essentially. He had a whole bunch of other contributions that I'm not even going to talk about. But one interesting thing that I learned about him is that in his university time, he was a member of the Ghost Club, which was founded in early 1800s, and I think it's still going on today. This is a recent screenshot from their website, and they have a whole gallery of things that they've been investigating as far as paranormal activities go. And I was thinking, what if Charles Babbage didn't end up pursuing mathematics, but instead chose the Ghost Club and pursued ghost hunting? Maybe the ghost hunters would have been like inspired by his work there or something like that. And during his time in university, since he was very mathematically inclined, surrounded by other mathematically inclined people, they founded an analytical society, which was a group of students who wanted to advance the field of mathematics. And around that time, they had, back in the day, this I learned recently, they had things called mathematical tables. And these tables were pre-calculations of various equations that one needed for their work. It would have been used for navigational system, for example, for doing on the sea. They would look at these mathematical tables so that they don't have to do the complex calculations. They would just look at the results with the variables that they choose. And the French government did something back then. They chose 2-3 mathematicians. They took all of the equations that needed to be calculated and simplified it all the way down to the bottom to about 80, 90 people who completed those equations with just subtractions and additions. And this was a point of inspiration for Charles Babbage, but he thought that this could really be done much faster with machines. And he really got a taste of this mathematical tables and how error-prone it is when he started in the Royal Astronomical Society, where he was appointed to calculate the mathematical tables for the Nautical Almanac. That also included the navigational records for sailors. And around that time, he thought, there has to be a better way, so he started working on a computer called the difference engine. This was only meant for solving specific problem, polynomial equations, and he actually was able to get some funding for this, got some government funding, but the engineer that he was working with, at the time he was a very accomplished engineer, but he had particular ways and he demanded too much money. Things got ugly and the project ended up being scrapped. But later on, you'll see from the photos that all of these ended up being built. And as the difference engine failed, he looked into creating a different kind of machine. He called this the analytical machine. And you can see all the numbers, they have their descriptions over there. This analytical machine had a storage system, a screen where you can print stuff. That's where you see Lady Ada Lovelace there. And this was really one of the earlier examples of modern computer because it had even branching and looping and various other things that was used for programming at the time. And it was programmed using punch cards. Sadly, this wasn't built either, but he ended up influencing a book called The Difference Engine, which I learned when I was researching this, apparently laid the foundations for steampunk genre. And I added it to my list. I want to read it. It seems interesting. Talks about what would have happened if the difference engine and the analytical engine ended up being built. Since we were talking about the first computer, we have to talk about the first computer programmer. And you already probably know about Lady Ada Lovelace, and she was the first computer programmer. She exchanged notes with Charles Babbage, and that's how she got inspired. But as I was researching it, I found something even more impressive by her, which I'll get to in the next slide. But she was born into a poet father and a mathematically inclined mother. But her father left him when she was 1 month old, and her mother wanted to make sure that she doesn't end up like her father. So she really wanted to promote her interest in math and science. And what was interesting about her, for me, when she was communicating with, exchanging letters with Charles Babbage, she saw the analytical engine as a way to manipulate symbols instead of just numbers. For Charles Babbage, you'll see it for the next few decades. All the names in these machines are very mathematically oriented. Statistical engine, differential analyzer. But Lady Lovelace saw this as a way of manipulating symbols. And in her note, she says you could program essentially a computer to create music for you, or images for you, videos for you, which is essentially these days what we're doing. We're just manipulating symbols. Fast forwarding a few decades, Alan Turing came to play, and he is very intimidating to talk about. So it was hard to pick things because all of these, especially during that time, because of the expansion of knowledge and the amount of money that's going into science, it's really hard to talk about all the advancements that they came up with. But he was an early prodigy, loved math and science, and was hated for it in his public school because they were more classics oriented. He met somebody called Christopher Markham who had a huge influence on him. They ended up being really close friends, and they influenced one another in their understanding of science. But sadly, Christopher Markham ended up dying because of TB. He drank a contaminated cow milk. And then as I was reading it, was that what if it was Alan Turing who drank the milk instead of him? Like, what would have happened? Like, all of these, again, the chain of events that we're seeing, one really determines the other one. After he died, he threw himself to work, did nothing else for, I think, the next few decades until he used his work as a way to cope with it. And in his university years, he built the Turing machine. And John von Neumann, we'll see that he's a genius in his own right, actually said, he was making comments about the Turing machine, and he said this machine laid the foundations for modern computers. And later in his life, he turned out to be Captain America because he was great at running. This I didn't know as I was researching it, and most people didn't know this at the time either. They only found out when he was on a run one day, and there was the running club, Walton Athletic Club. They had a group run. They were preparing for the Olympics. They were running marathons, and Alan Turing just ended up passing by them faster than they were running, and that's when they realized Alan Turing runs, and he's pretty damn good at it too. And later on, he worked on the Bletchley Park to crack the Enigma, along with other scientists that some of them we'll talk about later, and laid the foundations for artificial intelligence with his Turing test and the important papers that he published at the time. Another interesting, this one was an interesting one for me because he didn't just did hard science back then, he did soft science too. He wrote papers and also influenced scientific policy after the World War. He was very concerned about what would happen to scientists, especially the physicists, because all they did was related to war in during World War II, but he wanted to talk about ways of advancing science even after the World War, but for the betterment of it. And for that purpose, he wrote an article called As We May Think in late 40s. And in that article, he he mentions the way that the information should be disseminated to other people so as to inspire other scientific minds, because he says, for example, in the past, some of the scientific studies didn't make it to other people who could have maybe built up on it because they didn't have access to certain things. And that's when he talks about his idea of mimics, which is a hypertext editing system, essentially, where you can go from one link to the other, like Wikipedia. And as he's describing this, he actually describes the first Wikipedia doom scrolling, because he says you go from this link to that link, and he goes on it for a few paragraphs, which, again, was not an original idea, and it was inspired by another scientist, Emanuel Goldberg, and he had a machine similar to this called statistical machine, sorry. And again, they're still seeing computers or machines as a way of math and not necessarily symbols still. And mimics inspired Ted Nelson later on in the 60s to create the first hypertext editing system at IBM. And the image that you see underneath is an artist's illustration of what the mimic system would like based on Vannevar Bush's explanation in his original article. It was published in The Atlantic. John von Neumann, apparently it was a common saying back then that most mathematicians prove what they can. Neumann proves what he wants. And he did a lot of it. It shows why he was so brilliant. And game theory, quantum mechanics with game theory, he gave us a beautiful movie as well. But it was also ended up being used in a lot of these areas. Later on, he worked on von Neumann architecture. This is the original paper that he published, his store program architecture, which then later on inspired a lot of the upcoming computers of the time. And he worked on the merge sort algorithm, giving us one more thing to worry about for coding interviews. And then it wasn't enough. He then later on were the first people that talk about time complexity of algorithms, so that you have another thing to worry about. And for quantum mechanics, he laid the foundational mathematical foundations of computer mechanics with his book called Mathematical Foundations of Quantum Mechanics. Robert Licklider, and all these people live around the same time, but this one was especially an interesting one, like the other ones really, but in a different way, because Robert Taylor, Quinn will talk about, said that a lot of the things that they worked at Xerox PARC was actually Licklider's vision of what things could have been. And he says that there were not that many original work that they did. And one of the things that I want to focus your attention to is Project Mac and Multics and ARPANET, because these ones ended up influencing the likes of Ken Thompson and Dennis Ritchie along the way. Then they ended up doing more impressive things along the way. And his paper, The Computer as a Communication Device, also talked about many of the products or the systems that we're using today. Since Licklider was the funded projects and drive policy, one of the projects that he funded was Douglas Engelbart's project at Stanford Research Institute. And this one's as among the ones that I like talking about, because what he and his team did in 1968 was inventing the first computer mouse, and then they invented video conferencing, and then they did hypertext editing system that he implemented in their system called Online System. And then they also invented the collaborative editing. And this was all an hour and 30 minutes demo that I watched, and it was later coined the mother of all demos. I highly recommend it. I think it's a great way of seeing what the vision was and seeing that maybe they couldn't do it because of the technological limitations of their time. Another person breaking ground back then was Ivan Sutherland. Maybe it'll be familiar to you. He was essentially the person behind computer graphics, and I watched a recent interview from him. He said that most of the work that he was doing in his research, they weren't meant for utility or for usefulness, but meant for showing people what's possible. And he and his team showed people the first head-mounted displays. And later on, he built Sketchpad, which was essentially the first CAD application. He did geometric modeling on this. And you can see that there were different gestures that you could do and different tools that you could even run. And as he was working on this project, he actually used the first object-oriented programming paradigm. He implemented this with assembly at the time. There was no object-oriented programming. But his students knew what he was working on, and Alan Kay, which Quinn will talk about, was inspired by his Smalltalk programming language, was directly inspired by Ivan Sutherland's work. And many of the people that you see here were the students and went on to do amazing things later on.
Let's see if this works.
Oh, it works. Awesome.
Wow. Restarting works sometimes. So we just covered some ground on the theoretical foundations, and Furkan had mentioned some of it was lacking the technical capabilities to fully build out the vision. We'll touch on some of the characters that helped build that foundation, build upon that foundation. First one we're going to talk about is John McCarthy. He coined the term artificial intelligence at a research project at Dartmouth University, and also created one of the earliest high-level programming languages for artificial intelligence. At the first AI conference, now that as we know it now, this was the invitation he sent out and got some great thinkers to discuss on some of the proposal topics. I like how I'm gesturing here, but what you see is this. And this is a plaque at Dartmouth University commemorating this occasion with a group of the scientists that attended. 6 of these 7 people went on to do decades of computer science research or research in AI the years following this. As for Lisp, at the time especially, it had quite a few key components that made it very powerful and flexible. One of these was the macro system. This is a quick example of an AI joke that an AI created. And with macros, you can extend the capabilities of the programming language as well as build templates and edit, debug, test on the fly with its interpreter that does it in real time. Moving on to the world of algorithms, Dijkstra, someone we know probably quite well with his Dijkstra's algorithm for the shortest path. It helped me get to here today with Google Maps, and it would be a hard life without it. He also dived into structured programming and distributed programming, which I'll touch on a bit as well. After developing the Dijkstra's algorithm in 1959, this helped lay the foundation for network routing algorithms as well as GPSs and mapping applications. He moved on to structured programming in 1968, published the famous article, A Case Against Go-To Statements. Furkan and I were debating on the way here of the sentiment of this article, advocating for a more structured way because our brains can really only follow so much of the dynamic state changes that are happening in code, and it's best to rely on things like for loops, two or more use of for, than to try to follow with our human brains. And this led the way for structured programming principles of today. He also looked into distributed systems, and now known as one of the classic problems, the dining philosopher problems. And as shown, there's 5 philosophers with a fork adjacent in between each of the philosophers. And to eat, they need both forks beside them. And the challenge here is to make sure that no philosopher is starving while they alternate between eating and thinking. This led the way. It took a few tries of the ChatGPT to get this colorful, diverse image. It didn't like the original prompt, but we got there somehow. This laid the work for a lot of the distributed programming principles, and that helped with concurrency in programming, like semaphores. One fun thing that I found about Dijkstra is that his writing was known for its eloquence and his handwriting was known for its elegance. They were quite paired, and this is something that he hand wrote, but there's also Dijkstra's regular font if you want to have this in your treasure box online. Next, we're continuing on the path of programming languages a bit, especially the early ones. Nicholas Wirth created Pascal. And even though it's dwindled in popularity nowadays with more powerful programming languages like C++, back in the day, Wirth created this mainly with the target of teaching computer programming principles to new students or people who are not yet familiar in the field. He also wanted to release this as a public good and would send the source code to anybody who wanted it. Years after, it became essential for, I like my voice, but not that much, essential for teaching programming, and it helped foster good practices, especially in the realm of structured programming. Even though it's made for educational uses, some things like the Apple II computer, which we'll talk on a little bit later, and Lazarus, which is an open source IDE, used it in the beginning. Also in the realm of algorithms, Donald Knuth had created a book called The Art of Computer Programming. It's multi-volume. I spent hours on his personal website. Very interesting read. A lot of personality. It's a multi-volume book for A, 4B. Now he's on volume 5. And it is in-depth algorithm analysis, in-depth analysis of algorithms, words, that he went into this field with a lot of meticulous mathematical rigor and in-depth analysis. And this book is revered as one of the Bibles of computer programming, which I put on my list. I don't know if I will read the full thing, but it is an aspiration one day. Yeah, exactly. When I read it, we'll do a summary, a 1-hour summary next time. In 1970s, he was also frustrated with the lack of high-quality typesetting for academia papers especially, and so TeX, the typesetting system, was created, and we still use and see it in all the papers of today. He had his own Morris-Pratt algorithm, which helped with string search. Oh, one more thing. I just saw literate programming, and I want to give this a shout out because he advocated for the principle of literate programming, which wanted the code to be as readable by humans as it is executable by machines. And I don't aspire to be exactly like a machine, so I'm very grateful for all the more literable, maintainable programs that were built before me that I now inherit. An interesting thing that was a quote from Donald Knuth was that he had felt initially a sense of imposter syndrome, feeling like he was in a field where there was a lot of capable people and he wanted to feel belonged one day. And without a doubt, he, I think, has surpassed just belonging, but has been leaving a significant impact in the field with his algorithms and creating the big O notation, which is also something we worry about in interviews now. One fun thing, this is in his personal website that it was a wiki rabbit hole. Yes, there's a lot of wiki rabbit holes in my slides, but I'll give you a summary. He welcomes and rewards feedback, quite literally, for his multi-volume book. So for every mistake found, if you send it to him and it's accepted, he will mail you a $2.56 check. And it's $2.56 because, one hexamal dollar. He had to stop the actual mailing of checks because of fraud in stopped in 2008, but he sends now a check-like certificate from a fictional bank. And people of Reddit like to frame this as a badge of honor instead of cashing in, so that's quite nice. We talked a little bit about Ivan Sutherland and his object-oriented paradigm. Alan Kay, named as one of the fathers of object-oriented programming, created Smalltalk and later Squeak. Right here he's holding a prototype of Dynabook, which is an imagined portable user-friendly computer which looks quite similar to the laptops of today. Dynabook was never built, but it laid the foundation for what we have now as laptops. In terms of small talks to squeak, that was a squeak. He was influenced by Seymour Papert. Thank you for supporting my jokes. Influenced by Papert's educational theories and wanted to create yet another programming language that was focused on for educational purposes. 20 years later, with a team, he then created Squeak, which is an open source version of Smalltalk with some more features like multimedia support, making it open source and more portable. Alan Kay spent some of his, especially beginning years at Xerox PARC in his research, and he speaks highly of this time of innovation, and especially with the influence of Bob Taylor leading the lab at the time. Xerox PARC, this Bob Taylor, and Quora. Alan Kay has a lot of, I don't know if you've read Quora. I haven't been on Quora that much before this. Reddit was kind of my go-to, but after this, I spent hours on Alan Kay's profile. I kid you not. He says, he talks highly about the protection that Bob Taylor gave for the researchers that were doing the work. And it draws parallel to me to the managers and the leaders that we have in our workspace that create the place that we can do our best work. Ooh, sound effects. Speaking of Quora, he is very active on Quora, trying to learn how to think better. And he, did I stop with the microphone? No, it's good. Oh, I hear my own voice. It's funny because people write in third person thinking about how Alan Kay would answer some of these questions, and he comes in and does his first person kind of answer. A lot of them are quite insightful, and there's even one where a high school student wants to get in contact with him for an interview, and he comes in and says, "Give me your Skype handle or Zoom link and we can chat," which I find interesting. So I spent hours on this because it was interesting in this Wikipedia Quora hole. Probably after this, I'll spend many hours more. The last figure for this section of pioneers who built on the theoretical foundations is Karen Spark-Jones. She developed IDF, which helped us a lot with search engines. She actually started out studying history and philosophy, I believe, and was a school teacher for a little bit of time until she went into computer science. And that's where she really got the ball rolling. She, at the time in the 1950s, there was something called TF, which is term frequency. It measured the how common a word was in a document. But with her work with IDF in the 1970s, we were able to then see how common a word is, but also how common that word is in the collection of documents. So words like the and and very and common would have less importance when weighed against the TF-IDF entire scheme. And that, as you can imagine, helped lay the foundation for search engines of today like Google and helping us actually get more relevant search results. So this helped with information retrieval, and a lot of the search engine algorithms, they're more advanced, but they are built on the foundation that was laid down by Jones. Oh, one more thing, thank you. She also did a lot of work in advocating for underrepresented communities in the field of computer science, and also urging us to think about the societal and ethical implications that our work does, not needing to think about it in our every move, but at least have it in the back of our mind of thinking about what this would imply. And her important quote, important to me, is computing is too important to be left to just men. Cool.
Awesome. Speaking of a lot more women in computer science and tech, next up we'll have Grace Hopper, Amazing Grace, Grandma Cobol. And did you know that Neil Diamond wrote the song Pretty Amazing Grace after her? He didn't, but I don't know if you know that song now. That fell flat. She was a computer scientist. She did a lot of pioneering work. She was a Navy rear admiral. And the reason she got into the Navy was because of World War II, she says, and also because her great-grandfather was a rear Navy admiral, and she wanted to follow in his footsteps. And she said if she didn't, then there would be hell to pay. And later on, a computer programming pioneer because she built the first compiler and COBOL programming language, and a first one called Flowmatic. And she retired twice because she was called back to duty because of the important work that she was doing. And she was effortlessly funny. I don't know if you've seen this before. I watched this as we were researching it, and she was just all matter-of-factly just sitting there being herself, and was probably funnier than most guests that they have there. And Letterman says she is more impressive than all the people that they have as a guest. And two highlights that I had here, I highly recommend watching. Letterman asks her how she knew so much about computers when she was working on the first computer, Harvard Mark I. She just goes, "I didn't, it was the first one." And it was hilarious. And she used to carry around wires with her to describe the concept of nanoseconds. And she would say, if an admiral asks you why does it take so long to send a message, she would say there's a very large number of nanoseconds between here and the satellite. And you can see a Hello World example for the Flowmatic, which was, she strongly believed in plain English programming languages because she didn't want people to use symbols for programming, especially after her Navy work. She got into business sector, and there a lot more people would complain, "I don't understand these symbols, I'm a business guy," and then she would say, "Okay, then let me create something new for you." And she later on created COBOL, which was used throughout and still used today for maintaining existing systems, but it's still alive and well after 60 years. And obviously she found the first bug, but I was thinking back to the difference engine that I mentioned from Charles Babbage. If that was built, if a bug flew into that, it would just die. So we would have bug-free computers, like that, the opportunity. Another pioneer of that time, of practice especially, Margaret Hamilton, she is among the people who worked on the Apollo guidance system and helped humans go to the moon and come back safely. She also later on did something that gave all of us our job titles, which is really nice, because she coined the term software engineering and did a lot of pioneering work behind the software engineering practices, and talked to people about how software engineering is a respectable job, goddammit, because of all the other engineers that she was working with. But she started her work in the MIT Instrumentation Lab. Just as an anecdote, she said around that time it was tradition for people to give them a work that they thought was impossible at the time, either because they didn't understand the program that was written or it didn't work, and she was assigned a program that she had to fix. She spent some time on it, and the developer who wrote it took delight in writing the comments in Greek and Latin for some reason. So she had to sift through all of that, but she ended up getting it to work. And she was one of the programmers in the Sage computer, and later on she was assigned to the NASA Apollo guidance computer as the lead programmer, and you could see the guidance computer on the right side of the slides. And during their time in that project, she spent a lot of time. She said that she would sometimes lose sleep. She would be at a party, she would realize a mistake that she did from before, rush back to the office to fix it, because lives were at stake and they took it very seriously back then. And during that time, she got to think a lot about error detection on fallback system, which later on, actually there was one problem that they had simulations for every little change that they were making. And one person accidentally triggered an error, and they said, our astronauts are heavily trained and they will not make that mistake, so you don't need to spend time on it. And she didn't believe them, so even though she couldn't get the time from the product managers, she just said, at least I'll put a note. So she put a note for astronauts to not make that mistakes, but they ended up making the mistake. But thankfully, the error detection system that they put in place was good enough that nothing significant happened. I thought about putting these people separately, Dennis Ritchie, Ken Thompson, and Brian Kernighan, but their work is so intertwined, I thought it makes more sense to mention them all together, especially in one diagram. And if you remember back to Licklider's funding projects back in the 60s with the Project Mac and Multic system, Ken Thompson was a researcher in those projects, and he later on, along with Dennis Ritchie, created the Unix operating system and then the C programming language. And Brian Kernighan, in a recent, I think 2 years old interview, mentioned how many of the ideas that they implemented for the Unix operating system was actually inspired by the things that they worked on in Project Mac and Multics operating systems, which were time-sharing systems at the time. Licklider had a soft spot for time-sharing systems. And Brian Kernighan, Dennis Ritchie wrote the first free programming language book, which gave us the Hello World examples that I showed you from Flowmatic and COBOL. And they also wrote many of the fundamental Unix utilities that we still use and rely on today. Bjorn Strastrup, after the C, they needed class. Sorry? Right? It was very hard to find information on. And I got lazy. I'm like, people probably don't know. I guess I don't need to tell them much. But to my surprise, he's actually a computer scientist, because when you hear about him, you usually hear him in terms of C++. His name is attached to C++ now, and it never occurred to me that he is the freaking computer scientist. He also did work too outside of C++, and you can see that his research interest there with distributed systems, performance, reliability, and design. And he's the reason Mike is sitting there organizing this event for us. Thank you. Richard Stallman, I included him because of this. In his time in MIT in the 80s, he said that a lot of people were sharing code at the time. Whenever they would work on something new, they would maybe sometimes ship out the disks and whatever. But in his circle, he said that he claims that they were doing this a lot more often than other people. Later on, he got into distributing. He worked on Emacs and wanted to make some money off of it with free software, because he didn't have a job at the time. So he distributed Emacs for a few years. Later on, founded Free Software Foundation, the GNU project, would end up developing GNU Emacs, GNU Unix, compiler collections with GCC and GDB, and all the other tools that I'm sure some of us are using, maybe not all of us right now. And Linus Torvalds, I believe Linux, since he built Linux in his university years in the 90s, he made it open source 1 year after, and I believe it's among the biggest open source projects that was managed. And he also, after creating the Linux kernel, growing into something bigger, he built the Git version control system, because I think they were using BitKeeper. They ran into some problems because it wasn't free anymore. And I heard about how frustrating it was to deal with other code versioning systems from my coworkers. I'm definitely thankful that Git is here, even though from Kate's talk this morning, it's had its own quirks, but still it's definitely an improvement. And he also did a lot of advocacy for open source, and his work now is essentially used in everything that we're using today, which is a great impact. Another thing that he was sadly known for was being a jerk for very many years. And I had been noticing a trend in his videos in the last few years. He seemed milder in his speaking and his responses, and I don't remember reading anything outrageous from him in the last few years. And as I was researching, I found this, turned out that he actually apologized for his attitude from all those years, all the people that he scared away or essentially abused in a way. And he sent this as an email, a long email to the kernel mailing list. You can see the source there. And I thought that was really nice from somebody who's that prominent. He has the power, and he still apologized for it. I think that set a very good example for the rest of us.
So we've talked about a lot of the technology that came to be based on the theories. We'll take a quick look at the infrastructure that allowed us to be connected and give more access to people outside of the computer scientists especially. First person we'll look at is Robert Noyce, also called the mayor of Silicon Valley, which we'll know why in around 10 seconds. He created the first integrated circuit in 1959. Before that, he had joined the Philco Corporation and Shockley Semiconductor Labs under William Shockley, and there created a formative experience, a very rigid management style. 7 of them left. 7 of them plus him left, and they were named the treacherous 8, and they went on to create Fairchild Semiconductor. And there, they learned from the rigid management style from Shockley Semiconductor Labs and created a much more open environment, more egalitarian, flatter autonomy, more autonomy, flatter hierarchy. That's how we want it. And that helped with the innovation and flow of ideas. When he created the first integrated circuit in 1959, Jack Whitby at Texas Instruments also had a breakthrough. They did it independently around the same time. Very cool coincidence. And later they raced to create the first commercially viable integrated circuit. Almost a decade later, he went on to found Intel with Gordon Moore, and there he expanded on this open model and Intel became the model of an open atmosphere, open work experience, where autonomy, flexibility, the characteristics of Silicon Valley companies, and most of the tech companies that we enjoy working now base that model off of. And we are grateful for his contribution in that, in addition to this integrated circuit. Speaking of Intel over at IBM, a few years later, there was actually more than a few years, a few decades later, there was Mark Dean. He has 44 patents, which I will not list today, but I will focus on a couple of the main ones that really opened us up for PCs. He had he co-created the ISA bus, which allowed for peripherals to connect to the PC, and that opened up a whole new way for computers to be more modular. This also allowed for the computer graphics adapter to have color displays in PCs, and without the peripherals that ISA bus had allowed for, the color graphics would have no adapter, it would be on its own. After that, he also worked in shared memory data processing and optimized the performance, which led to the first gigahertz microprocessor, at that time a significant advancement in processor speed. And later in the last decade or so, he had been working on neural networks and real-time monitoring of them. And he has since retired, I think, from a professorship at the University of Tennessee, where he enjoys teaching a new generation of computer scientists like him. Next, we're going to take a look at the internet and how it came to be with Vint Cerf and Robert Kahn. They co-designed the TCP and IP protocols in 1973, and this graph is trying to tell you how it came to be. There were a lot of diverse, heterogeneous, that's a big word for me today, of networks, and they weren't able to communicate with each other. And so Kahn at the time envisioned a more open architecture and enlisted Cerf's help, who was a networking expert. So together they came up with TCP IP and also invited global network experts to come and weigh in on the proposal. And then they introduced this in 1974. After that, that enabled a network of networks, and they could communicate with each other even though things were on different networks. They were finding a way for a flow of information in a more flexible way. But TCP and IP alone wasn't enough. That helped with reliable data transferring, addressing, but there were some missing elements, like the user-friendliness of access. Most people at the time was using CLIs. I know most of us in the room probably love CLIs for some things, but my 60-year-old mom does not want to doom scroll on a CLI, unfortunately. So that was missing, and then a couple of other things like information, there was no way to structure it, and then interoperability was also an issue. And here comes Tim Berners-Lee, the inventor of World Wide Web. So at the time in 1980s, the main problem at CERN, the research institute he was at, was there was a problem with scientists sharing information. And so to tackle that problem, he proposed the World Wide Web with HTML, which allowed for the organization of information, as well as URLs, which helped with locating documents. And the first website went live in 1991. And that was the beginning web as we know it now. Later on, in 1994, he also created W3C, which helped with the ensuring open standards and accessibility for internets. In recent years, he started looking into having a more free and open web. The Solid project helps with giving user the access and the ability to choose what data to give, who to give it to, for what purpose. And even though Solid hasn't gained as much mass popularity as the World Wide Web has, they are open source and they are hiring.
All right, now that we have all that stuff built in, somebody else can come in and build things on top of those things that they built, which were built on top of the other things that other ones built. And we'll go through a quick list of people who created some of the influential technologies that we're using today. Ray Tomlinson implemented the first email program in ARPANET in 1971, and the first email that they sent was one small step. It was just hello. I think it was even a typo in hello. They were trying to type in hello or login, but only 2 letters made it into the email, and they ended up sending it. And they say that it was one of their regrets, but maybe they should have made it more significant. Steve Wozniak created the Apple I and Apple II computers. And then we have Daniel Bricklin and Bob Frankston in 1979 building the first spreadsheet program, VisiCalc. And this was also the first program to use the design system where you create the software based on the real-life physical object, which was especially, well, when iPhone first came out, for example, around that time, it was very popular to ease people into the digital world by using metaphors of real objects in UI design. Sophie Wilson co-designed the ARM architecture in the 80s along with Steve Ferber, which is now used in laptops too. Essentially all the embedded devices are running this because of its low energy requirements. Steve Wilhite created the GIF format in 1987, so I can share my favorite GIFs with people. And that was also possible, he just didn't do that out of nowhere. He was actually relying on Nasir Ahmed, who invented the discrete cosine transform, which was the most common used transformation on encoding and compressing media images. Sorry?
Sorry, I think GIF doesn't use DC. I think JPEG does.
Oh, it doesn't?
I think GIF is LZ.
Maybe. Thank you.
We have a slide about this later.
Yeah, we have a slide about this later. Thank you. Jarkko Oikarinen created the IRC client and server in 1988. Phil Kotz created the zip format, which made it a lot easier for people to download stuff from the internet. Henning Sjöldren created the session initiation protocol, which is, it is used for voice over IP, correct? I'm just kidding. It is used for voice over IP technologies. And Justin Frankel, when I was using Winamp, like I didn't know anything about programming back then, and I just assumed that they were there just on their own. But this was the first time that I didn't even know who wrote the program. As we were doing this research, I found out. It's pretty impressive. And he also went on to create a peer-to-peer network protocol in 2000 as well called Nutella. John Combe and Brian Acton, I included WhatsApp because of its wide adoption, but think pre-Facebook WhatsApp, not WhatsApp now. Ward Cunningham, he developed the first wiki. Then he thought that putting everything in one place is too much power. Now he started a project called Federated Wiki to federate the wiki itself, to distribute that information, and co-authored the Manifesto for Agile Software Development. And he didn't name this. Whenever I see somebody's law, it's usually other people naming that after them. So this was also not named by him, but he says it's faster to get an answer from people when you post the wrong answer rather than asking the question.
This is an overwhelming graph, but it was here. We put it here just to show the overlapping of minds and people and in the spaces in the past more than a few decades, and the shared space that gave space to the ideas, who then gave the power to the people to develop these ideas, to make them come to life. And it's really cool seeing how these great minds had intersect in different paths during their time. This is a blank slide for your pleasure. Do you want to go back to it?
Yeah, I'll show it briefly. We tried to create a graph. This is the one that I showed in the beginning. And this is an interactive graph. And at the end, you'll see a QR code to the presentation. We tried to fill this out to the best of our abilities. And by hovering over these nodes, you can see how these influences go from one person to the other. And we stopped it over here. If we didn't, this would turn into madness. And I didn't want to spend the time for it. That's why it's not there. But these network of influences from one person to the other, it really doesn't just end there. It all the way comes here. I think I could go in there, edit some of the lines, and essentially create a line from me to maybe Charles Babbage, all the influences that ended up with me having the job that I have today. So This was a journey, like, thank you for pointing out the mistake. This is exactly what we were going to say, because this was a journey for us as well, because we asked the question, this was something that we didn't know in the beginning. We asked the question, how did we get here? And we wanted to, together, we did our research and to the best of our abilities, try to find out how we ended up in the space that we did. And the story of computer science is not just a story of machine and code, even though it'll be, especially during the World War times, because of all the new computers that are coming out, giant, lumpy machines, it just makes it feel cold. But there's warm people behind them. A lot of them have families and different stories behind them. I encourage you to, if somebody here caught your interest, I encourage you to look into them more. Especially Grace Hopper, watch that Letterman video. It was awesome. And it helped us gain a different appreciation for even our current lives. I could trace, for example, my current situation in my career back to a few stays with my coworkers, like some of which are here, some of whom are here supporting me. I appreciate it. With their help, I gained certain knowledge and all the other influences that I had from different conferences, and that's why I mentioned Mike here as well, and everybody, all the volunteers here. When it brings us together, that even branches out, that graph ramifies in different directions, and definitely, hopefully, like Karen Spark said, helps us think about the ramifications of our work and maybe help us build a better future for everybody. Thank you so much for listening, and thank you for pointing out the mistake. But if you see other mistakes, you can create a PR, and if you notice it, we won't give you money, but we will give you a gift. Thank you.
I don't have much to say except for I think there's a through line from Ken Thompson to the Go language. Yeah. So in the next version, we can spin the web further.
One thing to mention is at least some of these people you mentioned, specifically, I'm thinking of Ward Cunningham. You can like follow them on social media like right now. They're still saying really like profound and interesting stuff. And for me at least, it was worth taking the time just finding them on different social networks and just following them. And you just get a feed of like insight, basically.
Sorry, this one's actually a question. Well, because I'm old, certainly not all of this material, but this flavor of material was something they did cover in university. To what extent do you think they're doing that these days?
I can probably answer that because I wasn't alive when the World Wide Web first website was live. So university is pretty recent, but in the essential courses, none of this, except for algorithms, but like Dijkstra's algorithm and specific ones were covered, but these people felt very, they felt like historical figures until I see them alive on social media and their personal websites, and that they're still talking about the stuff that they're passionate about, and then seeing their faces on the slides, it made them feel like, oh, they're a real person. They have this law, but they also are creating things. They're just another human, and some of them will jump on Skype with you to do an interview. So very little of it. I learned there's a much more human connection now, seeing their faces in this talk. Perfect cue. Thank you so much.